So today I'll be talking about superconductivity in twisted double-bilayer graphene, which is a relatively new system that has come about. So, twisted bilayer graphene has been around for a while now, and it needs no introduction. So you have one graphene layer, and you have another layer, and you twist them and stack them. And what this does is it leads to some remarkable properties, and in particular, it leads to some flat bands. Now, these bands arise because the twist modulates the electron tunneling between the two layers in a spatially periodic way. And for a small twist of a degree or so, the modulation wavelength is extremely long and can consist of thousands of atoms. So what this does is it allows you to produce strong correlations on demand in sort of like Lego fashion. And the system interestingly exhibits both superconductivity and correlated insulating behavior, as is shown in a couple of these papers here. What's more interesting is that if you look at the phase diagram, which shows the coexistence of superconductivity with correlated insulating behavior, that is reminiscent of the cuprate phase diagram, which has the superconducting domes. So this raises the question that can twisted bilayer graphene be used as a proxy which is clean and tunable to study the enigmatic cuprates? Now, more recently, there is this new system, which is twisted double bilayer graphene, where you take one bilayer and then another second bilayer. So each of these consists of two layers, and there are 4 layers in total. Twist them by an angle, and then you stack them on top of each other. So there were experiments from Philip Kim's group at Harvard, published at MIT and in Beijing. And what they showed were signatures of correlations, strong correlations. And in particular, the gap of this correlated insulating phase was seen to increase with an applied magnetic field, which indicates ferromagnetic order. Now, although this correlated insulator is interesting, we will not be talking about it today. What the focus of this talk would be is the superconducting state. Okay. And all right. So on doping electrons away from the half-filled insulator, superconductivity emerges. And in the system, it's found to be very fragile. It's very sensitive to doping, and it disappears if you move slightly away from optimal doping. The superconducting critical temperature was found to be of the order of a few Kelvin. But what's more interesting is that the superconducting transition temperature is found to increase linearly with the weak in-plane magnetic field. And this is a strong indication of triplet pairing. So the question that we ask today is that what is the order parameter and the mechanism of superconductivity? And this is a question we explored in these 2 papers. This work was done with Matthias Schroeder. Right. So in this talk, we'll be talking about the classification of possible pairing states in this system. So motivated by the recent experimental signatures of triplet pairing, we'll pay special attention to the triplet channel and possible mixed singlet and triplet phases. In particular, we'll ask under which conditions can singlet and triplet mix, and which triplet states transform into which singlet state. We'll look at the behavior in a magnetic field, and we'll also talk briefly about the microscopic mechanism that leads to superconductivity. All right. So before proceeding further, let me just quickly state the symmetries of this model. So irrespective of whether you stack the bilayers as ABAB or ABBA, you have a C3 symmetry because the lattice is invariant under 3-fold rotation perpendicular to the graphene sheets. There's also an in-plane C2 rotation symmetry, but this is broken by an electric field that you need to tune the band structure. All right. So our formalism would be that we are considering Cooper pairing with of net momentum 0, and our superconducting order parameter is what we denote here by delta alpha beta, which is a matrix in spin and valley space. And we can always decompose this into a singlet channel and a triplet channel. Okay. So given the strong coupling nature of the problem, we want to exploit symmetries without first considering the microscopic details. So now, what are the symmetries? We've talked about the C3 here, but there's another symmetry, which is SU2 plus and minus, corresponding to spin rotation in the 2 valleys. This is independent spin rotation, but there may be a Hund's coupling, which weakly breaks this SU2 plus cross SU2 minus down to SU2S, which is global spin rotation of all the valleys. Okay. So the main idea that we'll be using is that physically distinct superconducting states correspond to different irreducible representations of the symmetry group. Now, C3 has two different representations. There is the real and one-dimensional trivial representation, which is A. So suppose we introduce a small Hund's coupling term, which takes us away from this enriched symmetry limit. We can either have a singlet state or we can have a unitary triplet state. The way we calculate this is by writing down some generalized Ginzburg-Landau expansion for the free energy and then minimizing it, consistent with the symmetries. But there's also another possibility which emerges, is that you can, starting from a different parent SU2 plus cross SU2 minus invariant state, you can also have a non-unitary triplet state. And one may wonder that can there be mixed phases, which is an admixture of singlet and triplet? And on including terms in the Ginzburg-Landau free energy expansion that couple the singlet and triplet, we can answer this question. So for instance, in the first scenario, there is no admixture, but in the second case, you do find an admixture of a singlet with a unitary triplet state. Now and this is interesting because singlet and triplet are mixing here in the absence of spin orbit coupling. Now one may wonder what sort of band structure would favor the scenario A over scenario B or vice versa. And if you look at just pure low energy mean field theory, we'll always find that scenario A is favored. However, if we consider strong ferromagnetic fluctuations on top, we can see that scenario B is possible. And a quick comment that all of these states are fully gapped, except for this triplet state for which one spin species can be gapless. Now, the next natural question, given the experiments, to ask is that what happens if we add a magnetic field? So the way to expand these phase diagrams or visualize them is to add a third axis, which comes out of the plane of the slide in this case. And that can be your magnetic field. So suppose we include a magnetic field term now, and starting from each of these four different possibilities, what are the phase diagrams that we obtain? So in one case, we see that we have two triplet cases, and in both of these triplet cases, we see that there's a linear increase of TC with the magnetic field. So the first case is reminiscent of the helium-3 scenario, which was proposed by Ambagaukar and Mermin a long time ago. And more interestingly, this has been observed recently in lanthanum nickel carbide. However, for the first two cases, even though when singlet appears, this region is relatively flat, experimentally it could be that this region is really small, which is why we see a linear rise in TC nonetheless. All right, so next we can talk about superconductivity in the complex representation, which is E. And in this case, there are many more options, as we will see. So firstly, we have a nematic singlet state and a chiral singlet superconductor. And this is just the singlets. Now we have 8 options for the triplet states and 6 more for the admix states. And you might think this is a whole zoo, but how do we separate out the interesting ones? So if you look at a low energy mean field theory, we see that the states favored are this B state, which corresponds to this Balian-Wertheimer kind of state from liquid helium, and this chiral unitary state. Here xk and yk denote complex functions that on the Brillouin zone that transform as x and y under C3. Now if we add small ferromagnetic fluctuations, we favor the B and this admixture. Now in the presence of a magnetic field, the states that are favored are this nematic non-unitary and the chiral non-unitary state, whereas again this degeneracy is lifted by strong fluctuations. So far, everything we've talked about is quite general, independent of any microscopics, but now we can ask the question that what is the actual nature of the pairing glue in this system? And to do so, we'll look at this continuum model that was proposed by Cuscino and several other groups, and we'll focus on this flat band, relatively flat band that hosts superconductivity in the system. So first we consider that the superconductivity is mediated by the electron-phonon coupling. So to do that, we write down a coupling of the phonon modes with the electron density in the flat band. And integrating out the phonon modes, we get some effective density-density interaction. Now we can write down a mean field equation for superconductivity, and diagonalizing it and looking at the eigenvalues of the kernel, we see that we can get a TC of around 1.9 Kelvin, which is consistent with experiments. But more importantly, what we find is that the leading instability transforms under the A channel and not the E channel, whereas the subleading instabilities transform under the E channel. Finally, in TBG, we know that there have been several studies on Cohn-Luttinger mechanism of superconductivity, and we can ask the question, can Coulomb repulsion provide the pairing glue for superconductivity? So to consider this, we use an RPA formalism and compute the Lindhardt function. And what we find is for a wide range of fillings, so here is the, Lindhardt function, and here's the renormalized potential. For a wide range of fillings, we see that for 1/4 filling, we have no superconductivity, and similarly for 1/3. Whereas once you get to close to 2/3 filling, the renormalized potential develops a trough, and this can lead to pairing even though the interaction is repulsive. In this case as well, we find that the leading instability transforms under the A channel, whereas the subleading transform under the E. On doping away from this filling to slightly higher filling, say 3/4, the superconductivity quickly vanishes. And this is strikingly similar to what people see in experiments, at least. So just to conclude, we have systematically classified and analyzed superconducting instabilities in TDBG. The A representation allows for one singlet, a unitary and non-unitary triplet phase, and one mixed phase, whereas the E representation allows for a plethora of different states. We've also looked at the microscopic pairing glue and found that although electron-phonon mediated pairing does yield a TC consistent with experiments, the dominant interactions that distinguish between singlet and triplet could still stem from purely electronic processes. So, thank you.